Neural networks. How do you make them, and how do they work? That's what I hope to help answer in this video. This video is split into parts. Feel free to watch the parts separately, pausing and doing things on your own as needed. Timestamps for these are in the description. Often, when you're making decisions, the choice comes down to a variety of factors. For example, should I wear a coat today? The decision could be based on the temperature outside, how windy it is, if your parents ask you to put on a coat, and if you're going outside at all. These different factors all probably have a different level of effect on the outcome, or weight. We can arrange this decision weight system into what's called a perceptron, which is modeled after a neuron. You've got a series of inputs, weights that say how much inputs affect the value, a bias for more decision options, maybe you'll always want to wear a coat unless there are other factors, and finally an output. This output is put through a function called the activation function, so that the perceptron has a level of activation and doesn't reach unreasonable values. When you write out the equation for a perceptron mathematically, it looks like this. Perceptrons can have all sorts of activation functions, and you're free to tinker around with the one you use, but the one I'll be using is the sigmoid function. For consistent notation, I'll be representing a perceptron like this. Other people may use different variables, but generally the parts are the same. Perceptrons have some limits. Let's say you're trying to use these things to represent binary functions, for funsies, and you're messing around with the weights and biases, trying to match up the binary functions. This system works great for some functions. The OR function works, the AND function works, and the NOT function works. But when you get to the XOR function, it seems impossible to only get the correct values inside the activation region. And that's because the perceptron can only ever draw a straight line. If we go back to the equation representation, this makes sense. We aren't squaring anything. The only relationship we ever have between the variables and the weights is a linear one. Back to the drawing board we go. If our device isn't working, what do? That's right, we add more of the same thing. As a wise person once said, good design is doing the same thing, but larger, and expecting a different result. So our new setup will have 3 perceptrons arranged like so, and now I'll try adjusting the weights. And there we go. Perceptrons are modeled after neurons, and a set of perceptrons forms a web of connections like a network, so I guess you could call this. Let's review the anatomy of a neural network real quick. Feed-forward neural networks have a set of inputs and a whole bunch of layers that connect up. The inputs go into the perceptrons, cause a level of activation based on their weights and biases, and then those inputs are fed into the next layer, and the next layer, until they get to the end, in which case those are the outputs. It's called a feed-forward neural network because, well, the inputs are fed forwards one layer at a time. Another important term to know is the loss of a network. Often it's useful to know the difference between what the network calculates and what it was expected to calculate, so what the correct output is. That difference is called the loss. There are different theoretical ways to calculate loss, but that's what it measures. The thing that distinguishes the networks from each other, apart from what's in the perceptrons, is their architecture, or how the perceptrons are arranged. You can visually see the difference in architectures and maybe think about the limitations of different architectures. There's also different types of networks, but I won't be covering those today. Here's another diagram. Calculus can be scary. When I asked my friends if they thought calculus was scary, they said no. But it's scary to me, so I know that it's possible for calculus to be scary. The point is, in order to really understand how neural networks train, a little bit, a tiny piece of calculus is required. Let's step through that together. First, a derivative. It's essentially a fancy word for the slope of a graph, or the rate of change. If the rate of change is 0.5, for example, you know that for every unit you move in the x direction, you move 0.5 units in the y direction. We write the derivative like this, meaning the derivative of y with respect to x, which can be a little confusing because it's not actually division. Don't worry about it too much. You just need to know that this means the derivative of the top thing with respect to the bottom thing. The derivative of a function can also be represented by a tick mark if that function only has one variable. There are some tricks for calculating the derivative. If you have a power, for example, you can just grab that power, pull it down, and then subtract 1 from the original power. If you have a circular function, like sine or cosine, your math teacher will tell you to memorize this pattern. Let's say you have a set of functions, and you want to know the derivative of y with respect to x. As x changes, how does y change? You could substitute x in and then expand that out, but that's long in a lot of terms. Enter the chain rule, which says that the derivative of a composite function, 2 functions chained together, is the derivative of the outer function multiplied by the derivative of the inner function. If you know the derivative for all the different links in the chain, in this case, y with respect to u and u with respect to x, you can multiply them together to get the derivative of y with respect to x. Since u is a function of x, we can substitute that in and do this visually. Let's talk about Newton's method for calculating zeros of functions. The way it works is you take some function, and you essentially pretend it's a linear function. Start by picking an arbitrary point, then use the slope of the function at that point to calculate where it would hit the x-axis. Then go to that new location and do the process again. It works surprisingly well, but sometimes bounces around, especially if there are no actual zeros in the function. But what if, instead of going all the way to 0, we just try to go a certain percentage of the slope of the function? Say 1/10. So if the slope is 2, we'll travel 0.2 units down. Then there's less bouncing, and we converge to a local minimum, even if it's not actually 0. In order to train the neural network, we need to first have a perspective shift. Instead of looking at the network as fixed, with inputs causing the outputs, we'll instead fix the inputs and outputs in place, and use the loss as the output. The neural network is a giant equation, because a given input will always give the same output. Each weight and bias is now a variable in this equation, and this modified Newton's method can be used to find the local minimum loss, which means closest to the expected output. I've drawn this equation as two-dimensional, but it's important to note that every weight and bias is an independent dimension. They can all be changed independently to affect the loss. So the loss function can be modeled as a high-dimensional blanket. This loss can really be set to whatever you want, as long as it gets closer to 0 when the outputs get closer to the expected outputs. The loss function I'll be using is this, which has a few good properties. The 1/2 in front cancels with the square when taking the derivative of it, so no further multiplication, as well as this. The squaring means that the slope essentially encodes how far away from 0 you are, comparing the graph to, say, an absolute value function, where the slope only tells you which half of the function you're on. This has more information. Just to go over the basic algorithm again, we figure out the error of the network, then we figure out the gradient, then we adjust each weight and bias by that gradient, multiplied by some constant, so the process doesn't spiral out of control. Okay, now I'm going to walk through deriving the backpropagation algorithm. For every different variable we want to change, we need to know how much that variable contributes to the final output, which means the derivative of the loss with respect to that variable. First, let's start with a weight on the final layer. We have the function for loss, and while expected is a constant, actual is a function. So let's add actual to the chain and step into that. Okay, well, x is a function, so add that to the chain. Okay, and now we've gotten to the end of the chain. Weight 1n is the goal weight, and all those other things don't contribute because they don't have weight 1, so they can just disappear. Now that we have our chain, we just need to fill it out. That's the gradient for weight 1. To backpropagate through weight 1, just compute those values, multiply by the training weight, and add it to weight 1. Then the error is reduced. And I know this formula is going to be different for every weight and bias, so what was the point? Because this can't be translated into code. But I'd like to point out a pattern. If a different weight on the same node had been chosen, the formula would look the same up to Q1, which instead would be Q2, because it's a different weight which points from a different node. Okay, what about a bias on the final layer? It's the same formula, minus the node behind our checking node. Logically, that makes some sort of sense. The biases are connected to the same things that the weights are, except for that node. How about one layer back? Now the weight affects both errors, so both of them are factors. Okay, let me do some rearranging here, bring like terms to the front and all that. And thinking about it, this bit could generalize. If there are more than 2 neurons in the last layer, there would be more than 2 values added together here, because they all connect to the target neuron in the same way. The second layer bias has the same formula, but like before, without the connection to the previous layer. So just put that summation in there, and simplify the formula, and voila, a gradient calculation that works for any layer. Since all the layers before this one have the same structure, those can be skipped, but please do them on your own if you want to. We can calculate the derivative, the gradient, for the last layer by using this formula, and then when we have that, we can use the set of the gradients in that last layer to find the gradients for previous layers, and continue backwards all the way through the start. One last thing, in order for this formula to actually make any sense, we have to know what the derivative of the activation function, this friendo here, actually is. The activation function I'm using is the sigmoid function, which is 1 over 1 plus e to the negative x. So let's calculate the derivative of that. First, fix that whole 1 over thing. 1 over a number is just that number raised to the negative first power, so put that in, and then we can use the power rule and the chain rule. E to the x is special. The derivative of e to the x is still e to the x, so I can just yoink that negative sign and simplify, and then more algebra. And there it is, the derivative of the sigmoid function. I am not going to show any actual code in this section, but this will be a detailed walk through the algorithm, showing what needs to happen in one iteration of backpropagation given what has been covered already. First, start with forward propagation and save the states of the nodes for use in backpropagation. Second, the actual backpropagation part consists of calculating the gradient for each neuron in the target layer, and then multiplying each weight and bias by that gradient. After completing a layer, move back to the previous layer. Two important things to note. The first thing is that error calculation is different for the last layer. Remember that there's no summation because there's already a set value for loss. The second thing is that the algorithm requires the weight and bias values, so make sure that when you're changing them, you do it in a way that doesn't also affect the calculations. Neural networks are a web of perceptrons, but they can also be represented as matrices. If you're converting a neural network to a set of matrices, the first thing to notice is that matrices are rectangular, whereas a neural network is lumpy, so it needs to be broken down into a set of matrices. There will also need to be separate bias matrices and weight matrices. Representing the network as a set of matrices allows for some pretty cool tricks. For example, let me put the equation for a perceptron up here on the left, the matrix representation of the example network on the lower right, and then just draw out matrix multiplication. The equation for what goes inside a perceptron is matrix multiplication, minus of course the bias, but that means stepping through an entire layer is as simple as doing a matrix operation, followed by some pairwise functions. If you still don't understand feed-forward neural networks completely, that's okay. When I was learning this, I spent about 2 weeks just trying to figure out what the network was even doing. I highly suggest using pencil and paper to draw out a network and derive what it should be doing, as well as asking for help. Here's all the numbers for an example network, stepping through one iteration of forward propagation and back propagation. It's a bit tedious, but walking yourself through the actual process is extremely helpful in wrapping your head around what should be happening, as well as where any errors in your code could be. Feel free to ask me any questions in the comments as well, and I will answer them to the best of my ability.